Hello, today we're going to be talking about pH. So let's review the self-ionization of water. Water can self-ionize, so split apart into hydrogen ions and hydroxide ions. Now, if we're being more accurate, you'll have several water molecules together, and one of the waters is going to act as an acid and another one will act as a base because water is amphoteric. The one acting as an acid will give away its hydrogen. The one acting as a base will attract a hydrogen. And so that will leave behind their conjugate pairs, which the conjugate acid is H3O plus or hydronium, and then the conjugate base is the hydroxide. So effectively, hydrogen and hydronium wind up being the same thing when you have water solution where there's more than one water molecule, which is basically always. So we wind up with three types of solutions. You have a neutral solution where the hydrogen ion concentration is equal to the hydroxide ion concentration. Don't forget that those brackets means concentration or molarity. Okay. In an acidic solution, I have more hydrogen ions or hydronium than hydroxide, but in a basic solution, I have more hydroxide than hydrogen. Finally, we have this measurement of water because of how it can self-ionize. It can break down into hydrogen ions and hydroxide ions. Well, if I multiply the concentrations of those at 25 degrees Celsius, I always get the same value, 1 times 10 to the negative 14th. Very small number because water doesn't ionize very much. So I can kind of rewrite this statement here, plugging in the value for Kw, so that both of these always multiply to equal 1 times 10 to the negative 14. All of our calculations for this class will be at 25 degrees Celsius, so you don't really need to worry about that. This number only works at that temperature. We're going to do everything at that temperature. So now we get into these concepts of pH and pOH. pH measures acidity, which measures the amount of hydrogen ion concentration. So like how acidic is it? But pH uses the equation negative log of H plus. Don't forget that H plus ions or hydrogen ions are the same thing as hydronium ions in water. So these two equations are the same. Right? Now, because it's this negative logarithmic scale, right, you wind up with a pH scale from about 0 to about 14, with 7 on the pH scale being neutral at 25 degrees Celsius. If it's below 7 on the pH scale, below 7 will be an acid. Above 7 will be a base, because again, this is a negative logarithmic scale. So the larger the concentration, the closer that this pH is to 0. Now, the other side of this, pOH. pOH measures basicity or alkalinity, which is a measurement of the hydroxide ion concentration. So we get this pOH concept, which is the negative log of the hydroxide ion concentration. And again, because it's a negative log scale, you wind up with a scale from about 0 to about 14. 7 is still neutral on the pOH scale, but acid and base are flipped on the pOH side. So below 7 would be a base on the pOH because you have more hydroxides. But above 7 will be acidic because you have less of the hydroxides. So just kind of remember that these scales are flipped. The smaller the pH, the more acidic. The larger the pH, the more basic. And then flip-flop, the smaller the pOH, the more basic. The larger the pOH, the more acidic. So we can relate those four things using this calculation box. All right. pH and pOH always add up to 14 for the same solution at 25 degrees Celsius. So I can convert back and forth between these two by subtracting from 14. We've already looked at this equation. 1 times 10 to the negative 14th is equal to the hydrogen ions times the hydroxide ions. So if I want to go between hydrogen and hydroxide, I can divide 1 times 10 to the negative 14 divided by whichever one I have will give me the other. Now on these sides, if I have hydrogen, I can take the negative log of that value to get to pH. The reverse operation of a logarithm like that would be 10 to the negative pH. So 10 raised to the power of a negative pH will help me go backwards and get to the hydrogen ion concentration. Same idea on the other side, hydroxide ion concentration. If I take the negative log of that, I will get the pOH. If I want to go in the reverse direction, I need to do 10 raised to the power of negative pOH to get the OH concentration. So let's look at several examples here. It says, what is the pH of a 1.4 times 10 to the negative 3 molar H plus solution? So this is a concentration of hydrogen ions. The formula there is negative log of the H plus concentration will give me pH. So in your calculator, you will literally type in negative and press the log button. Some calculators will give you the parentheses automatically, some of them don't. But most of the calculators I have in my class are going to be, you'll type in negative log, actually let me use a darker color. You'll wind up typing negative log, and then the concentration, you can still use that E for exponential notation, like this. And you'll type that in and you'll get a pH. Now there are significant figures rules for logarithms. For this class, I'm okay with you guys just consistently using 2 decimal places because the sig fig rules for logarithms are a little involved. And I don't want you to focus too much on that part. Just solving it is good. So 2 decimal places is fine for pH or POH for this class. So here's another example. What is the POH this time of a 4.5 times 10 to the negative 8th molar H plus solution? There's no way to go directly from POH to H plus. Can't happen. We have to do 2 steps. I can use this first equation that pH is equal to the negative log of the H plus concentration. So I can plug in this concentration, take the negative log of that value, and I'll get the pH with my 2 decimal places. But it's not asking for pH, it's asking for POH. I know that we can add those 2 together to get to 14. So let me plug in the pH that I found, plus the POH, and then to solve and get POH by itself, I just subtract 7.35 from both sides to get my POH. Now for this third example, it says, what is the OH negative concentration, remember brackets for concentration, of a solution with a pH of 5.76? So in this case, I have the pH already. I know that pH plus POH is 14. So I can plug in the pH they gave us in the question and then subtract to get the POH. I want the POH because I know that the relationship between OH and POH is 10 to the negative POH. So I can now plug in this POH over here. And so 10 raised to the power of negative 8.24. And plug that in your calculator. There are a couple different, there's some different ways you can do it, but I think the easiest way is using the caret 10 caret negative 8.24 in your calculator like that, and you'll get the concentration. Now, some calculators are going to give you standard notation, which is okay with me, so 0.0000, oops. Like that, 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah. So these 2 answers are the same thing. This is just in standard notation versus exponential notation or scientific notation. Either way you want to write it is okay with me. I will typically write it in scientific notation when it's this small because it's shorter. Now for this fourth example, what type of solution has an OH concentration of 3.4 times 10 to the negative 3 molar? There are several approaches you could take for this. You could change this to POH and use the POH scale to classify. You could also change it to POH and then to pH and use the pH scale. I'm going to show you a different way that is also very valid. All right. I can use this equation here, the KW expression. 1 times 10 to the negative 14th is equal to the hydrogens times the hydroxides. I can plug in my hydroxide concentration here and then divide both sides by the 3.4 times 10 to the negative 3. That will get the hydrogen ion by itself, and I wind up with 2.9 times 10 to the negative 12. Well, what I can do is I can compare these 2 values. 2.9 times 10 to the negative 12 is much smaller than 3.4 times 10 to the negative 3 because it has that more negative exponent. So because the hydrogens are much, much smaller than the hydroxides, I know that this solution must be a base. More hydroxides, more basic. If I had more hydrogens, it'd be an acid. If they're equal, it'd be neutral. So that is another way that you might approach these classification questions. Finally, let's talk about a couple different ways that we can measure pH. We can use an indicator. An indicator could be a liquid, or it could be dissolved into like a paper, like a pH paper or a litmus paper, but they effectively change color at different pH values. So if you'll notice this chart here, the pH is at the top from 0 to 14, and then these are all different types of indicators. And they change to different colors at different pH ranges. One that is used very commonly in chemistry is phenolphthalein, which turns pink in this like 8 to 10 range here. That's a really common one. You'll also see we've used bromothymol blue before in class, which goes from yellow when it's an acid, very briefly green, and then blue when it's a base. So there's different indicators that change at different colors. It might be useful for different situations. There are also things called pH meters or pH probes, and those are calibrated to use the conductivity of the solution to measure the pH. And so that will give a very specific value on the pH meter and winds up being a little bit more accurate than just a color change.